What I want to do is provide from a low theoretical level, a practitioner's view on these embedding questions, right? And the most important thing to say is that this work has been done with some fabulous junior collaborators, Jiawei Zhang, who was an outstanding graduate student at Columbia, Ji Wang, who is an outstanding, and Alex Vitek, who are outstanding postdocs at CCQ, and Alex Hampel, also a outstanding postdoc at CCQ, as well as Jonathan Karp, whose work I'm only briefly going to mention, who is just finishing up his PhD at Columbia and is sadly moving to finance. And then some of the work was done with Jen Cano and Antoine George, who are faculty scientists at CCQ and other places. And some of the work is reported in the references which are listed on this page. Right. And by the way, these Zoom things are always a little awkward. I will not be able to see the chat, but if you have questions during the talk, please do interrupt me and I'll try to address them there. And if I don't notice you, well, shout louder. Okay. All right, so to start with a bit of what I would call apple pie and motherhood, I should say that I'm a theoretical condensed matter physicist and mostly attuned to trying to understand experiments. So a truism, I think, is that material properties are controlled in large part by the collective properties of interacting electrons moving in an environment defined by specific atomic configurations. This slide shows an example. Particular arrangements of copper, oxygen, and other stuff, I have shown two representations of a crystal structure, lead to a strange set of electronic phases and regimes, including superconductivity at relatively high temperatures, insulating and magnetic behavior, and other things which may or may not correspond to actual phase transitions to long-range order, but involve behaviors which are unusual from the point of view of traditional physics, right? And so what one would like to understand is the connection between these specific arrangements of atoms and these interesting properties. One class of properties I particularly like to highlight is shown on the lower right corner of the screen, and that is the electrical resistivity, right? And what is shown here is the electrical resistivity for a family of materials of the type shown on the left, and the temperature dependence to a conventional condensed matter physicist is unusual. And one of the things one would very much like to be able to do is to relate that temperature dependence to the collective properties of interacting electrons moving in environments defined by specific atomic configurations, right? Here's another example, which is a particular material, calcium ruthenium oxide, alloyed with strontium. As you change the fractions of materials, this thing goes from being an insulator at all temperatures, as seen in the upper panel. This is the electrical resistance, presented on a log scale, is very high, to being a metal at all temperatures. That's the blue trace at x equals 0.2, where the resistance is low and decreasing with temperature. And at intermediate concentrations, you see a transition from one behavior to the other, right? This transition is related to magnetic order. The magnetic ordering temperatures are shown by the little arrows, and in the lower panel of this figure, you see a measure of the magnetic properties on the same temperature scale. And part of the point of this is to demonstrate that the metal to insulator transition does not occur at the same temperature necessarily as the magnetic to non-magnetic transition. So these are kinds of behaviors that one would like to understand. All right, here is a new class of materials that I will get back to later in this talk, which produces an interesting range of phenomena that one would also like to understand. The jargon for these materials is TMDC, transition metal dicalcogenide, placed in a so-called Moire configuration, right? So basically, these are materials that exist in very weakly coupled, essentially monatomic or triatomic layers. just a small number of atoms thick, so you can think of them as truly two-dimensional electron gases. If you stack two of them, either two of the same material at a small relative twist angle, as shown on the left, or simply two materials with slightly mismatched lattices, as shown on the right, what you get is a structure which has a very large unit cell compared to an interatomic distance, let's say hundreds of times larger. Along with this large unit cell goes two very attractive features, or three. First, the electron concentration can be varied simply by electrical means over very wide ranges. You can change the number of electrons per unit cell from essentially 0 to 2, that is from a totally empty band to a totally filled band, just with electrical control, not doing anything else. The second thing is that this ability to change the size and shape of the unit cell means that both the electron dispersion and the strength of the electron-electron interaction can also be tuned over relatively wide ranges without, in principle, introducing much disorder. Right? So this tunability creates a opportunity to systematically compare experiment and theory, because now you have in situ a completely tunable material. Right? So this provides very interesting, I think, opportunities for quantum embedding theories. All right. Here, I think I'm going to skip some of the details of atomic physics and come back to this later. All right. Now, if you want to understand what interacting electrons want to do, well, in some sense, the basic theory was laid down almost 100 years ago by Paul Dirac in a paper he published in 1929, where he explained correctly that the fundamental laws necessary for the mathematical treatment of a large part of physics and the whole of chemistry are known. The difficulty lies only in the fact that these laws lead to equations that are too complex to be solved. Right? And he concluded in this paper, it therefore becomes desirable that approximate practical methods of applying quantum mechanics should be developed. Right? So that was 100 years ago. You may ask, why has it taken so long? After all, for the single particle Schrodinger equation, one particle in a specified potential, the solution is completely understood. This is a differential equation. If you introduce to it a short distance cutoff, then you can define a finite, although large, depending on your cutoff and your system size, basis of orbitals. In this basis of orbitals, this thing turns into a linear eigenvalue problem, and it's solvable for bases which are large enough to be practically useful. All right. Now, if you want to study a large number of particles, then you have to deal with a wave function, which depends on many particles, or if you use this discretization, a very large Hilbert space, typically exponentially large in the number of particles. All right. The second problem, as we all know, is that quantum statistics plus interactions mean that the particle coordinates are entangled, so these wave functions don't necessarily factorize in any interesting way. And the wave functions are complex and constrained in funny ways by Fermion statistics. So what this means is that meeting Dirac's challenge is really the ultimate big data problem. You have a system which is cast in a space of exponentially large dimension that you cannot deal with by brute force. Right? And the question is to find a manageable low-dimensional subspace in terms of which you can formulate and solve the problem. And embedding methods are one, in my view, of the ways of doing this. And what they really do is truncate the entanglement in interesting and physically useful ways. All right. So, but continuing with the generalities, and this was discussed at some previous points in the conference, one way to reduce the amount of information is to include correlations on the average via, for example, density functional theory. All right. Now, density functional theory compresses the information that you want to get in two ways. First, it says you should focus on a single scalar quantity, the ground state energy. And the second is it says that this can be obtained by minimizing a functional, not of the full wave function cast in a Hilbert space of exponentially large dimensions, but a functional simply of a scalar function of three space coordinates, namely the electron density. Right? They further said that this functional has interesting properties, and in particular, it's the sum of a part, which I've written here is an integral of v times n, which specifies the material you're talking about, and then another part which is universal, namely that it's, in other words, that it's the same for all materials. Right? The second important thing about this construction is that the minimization of this functional is accomplished via the solution of a single particle Schrodinger equation with a self-consistently determined potential. So it reduces the problem to one which has already been solved. Right? So it's compressed the information by two routes, looking at something which has less information than the full wave function, and obtaining that by looking at something which depends upon fewer degrees of freedom. Right. Now, I would like to formalize this, and formalization should be given in quotes. This is a physicist's formalization as follows. All right. There is a functional. You should view this as extremizing a functional of two variables. One variable is a potential, this Hartree plus exchange correlation potential, and the other is the density. This functional can be sort of schematically written as a sum of a trace log plus the thing I defined on the previous page minus something which is more or less a Lagrange multiplier. The trace log thing is really just the notation for solve the single particle Schrodinger equation in the presence of these potentials. All right. So if you demand that this functional be stationary with respect to variations both in the potential and the density, then you reproduce the equations of density functional theory. Stationarity in the potential says that you have to get the density right, that the density predicted by solving this equation comes out correct. Stationarity with respect to the density tells you the functional that's implied by the density. So this theory is formally exact, but of course we don't know the exact functional, and operationally we don't know the thing about the full functional that we really need. We don't want the functional itself. What we want is a recipe which generates this potential, VHXC, from a specified density. Right? So that's the thing which is not known exactly, and there has been many years of art put into identifying reasonable approximations to this thing. But that's what we want out of the functional, is a machine for converting a density into a potential. Also, of course, in implementing this, we need an efficient solution to the single particle Schrodinger equation, because to achieve self-consistency, we have to solve this many times for many orbitals. All right, so this is telling you what you already know. Now, if you want to go beyond this approximation, and especially if you want to look at spectra dynamics and thermodynamics, then you need a different formulation. The formulation I'm going to discuss in this talk is the Green's function formulation, which compresses the full information contained in the wave function into some sort of correlation function of operators defined in terms of the wave function. Right? If you go back to the set of basis functions I defined before, then this thing is a matrix in the space of single particle basis functions and is a function of time or frequency. And in the independent particle approximation, this matrix can be determined in the same way by solving the Schrodinger equation. All right. Now, if you wish to go beyond the independent particle approximation, then you need to understand how the Green's function is changed because of interactions. That information is encoded in the so-called self-energy operator, which is defined in the first equation of this page. It's essentially the difference, appropriately organized, between the full Green's function of your problem, the exact Green's function, and the non-interacting approximation to it. It's also a matrix in this space of single particle orbitals, and it can be expressed perturbatively, for example, in Feynman diagrams. Now, this is where the complexity comes back, right? We've compressed the exponentially large amount of information in wave functions into a function of order n squared, or m squared, where m is my number of orbitals, times a single function frequency. But to obtain this, we have to calculate a number of diagrams, which blows up factorially, in fact, with diagram order. Now, in fact, the minus signs associated with fermions cause lots of cancellations at higher order and reduce the total number of diagrams you have to look at from factorial to exponential. But still, a full evaluation of this is a exponentially large problem and not feasible yet. Okay. So this, to my mind, is where embedding comes in. Doing embedding means you take your single particle basis, you partition it into a correlated part and a background part. You treat the background part by a low-level, cheap, fast method. You treat the correlated orbitals by an accurate method, and you impose self-consistency. So therefore, to me, fundamentally, embedding methods are properly viewed as an approximation to the dynamical self-energy and all the other parts of quantum many-body physics that go with it. That's what embedding methods really give you, is a, you hope, useful and reasonably accurate approximation to the self-energy. That's their job. Okay, again, you can look at this from a formal point of view by imagining a functional which now depends not just on the exchange correlation potential, if you're building your embedding theory on top of density functional theory, and your electron density, but also on the parts of the self-energy you're going to retain and the corresponding Green's function. So you get a functional which formally has the same form. You again ask that it be stationary with respect to variations of all of these things. Stationarity with respect to the exchange correlation potential and the density give you back the equations of density functional theory, except that you have to use the full solution to evaluate the density. And stationarity with respect to the other two things says, in effect, you have to solve a correlation problem in the restricted subspace of the embedding problem. All right? And again, what you need out of density functional theory is a machine to deliver you this potential given a density. What you need out of the solution of your quantum problem is a machine to give you the self-energy once you've specified the correlated part of the problem. Okay, now, this is general. What's done in practice up to this date is the following, because we don't know what this functional is. All the embedding methods that I know about in practice say that this functional is a sum of two parts. One part is the background part, the other part is the correlated part, and then there is a, let's say, a double counting part to remove the things which are common to both. In the density functional plus dynamical mean field version of quantum embedding, what you do is, again, this says that you obtain the exchange correlation potential from your usual density functional theory, but using the particle density from your full approximate many-body solution. And then you have to solve a correlation problem to obtain your self-energy. Right. Just as a side remark for those of you who are electronic structure practitioners, the relatively widely used DFT plus U approximation is precisely this, with the correlated part of the self-energy solved in the Hartree approximation to this theory. Okay, now, to construct this correlated thing, what one typically does is pre-select correlated orbitals, typically using physical intuition based on states obtained from some density functional calculation. And the typical thing, but to my mind it is conceptually not at all required, is to choose the basis of states on which you want to impose correlations to be localized in unit cells. All right? And then you make a further locality approximation to the self-energy. Right? These two things are what's done in practice, but conceptually they're not necessary to the method. A crucial thing which is essential to the method is to project the interactions into the correlated orbitals. Right? Now, this is not as simple as just taking the Coulomb interaction you know and evaluating its matrix elements amongst the states that you chose to keep. Right? And the reason why not is that the states which are not included in your correlated subspace can act to screen the interactions. And screening is important. As you may remember from elementary electrostatics, if you have something which is in a screened environment, you change your basic Coulomb interaction, E squared over R, to something like E squared over epsilon R, right? And for typical solids, epsilons are 10 to 15. So if you want to get your interaction right within an order of magnitude, you have to deal properly with the screening. All right. So then, as I said before, typically one makes a locality approximation and solves the correlation problem in dynamical mean field theory or one of its cousins. This is a very extreme approximation, which says that in your orbital basis, the self-energy is spatially local. It's strictly valid only in an infinite dimension or infinite coordination number limit. And its usefulness in practice remains to be discussed. All right. So this approximation has been widely used, and a lot of the justification is a posteriori. Here's an example. A particular material on the left, lanthanum nickel oxide. On the very left-hand side of the screen, what you see in bright colors is an experimentally measured photoemission spectrum. This traces out essentially singularities in the electron Green's function where there are propagating electrons. The white curve is the density functional band theory's opinion of what this curve should look like. It crosses zero, which is the Fermi level in the same place as the exact theory, but gets the basic energy scales wrong by a factor of about 3. On the right is our calculation using this kind of embedding method. And what you see is that it gets the energy scales right. It rather underestimates the broadening, although some of that is badly represented by false color scales, and some of that is experimental broadening. Similarly, on the right, you can use these methods to compute things like whether the system changes from metal to insulator as a function of pressure or unit cell volume. And again, it gets things reasonably right. Right? But these are a posteriori justifications. We did a bunch of things, adjusted how we defined the correlated parts and the interactions, and then obtained good agreement. There are similar things you can talk about for other reasons. I will just say you can, because I'm probably going to run out of time, I'll just say you can read in this paper to understand more details or more specifics. Right? All of these things are a posteriori justifications of theories that inside them have many moving parts. First, you have to identify the orbitals that you want to be correlated. Here is an example, a particular material which is of recent interest in the context of superconductivity. For reasons that I can discuss afterwards, the orbitals which should be treated on a beyond density functional theory are the ones I've highlighted in red, and you need to pull them out from the total set of orbitals defined by a calculation which is shown in black. Right? Then you have to compute the interaction terms by including screening from other orbitals. Here is an example from a different material, just to say that the screening transitions that reduce the magnitude of the interaction are processes which are shown in gray, which involve transitions amongst orbitals which are not at all correlated, and transitions from orbitals which are uncorrelated to orbitals which are taken to be correlated. So this computation, by including just a restricted set of screening terms and only to some perturbative order, may be questioned. Okay, so given all of these uncertainties, it would be nice to have an experimental ground truth to which you can start to systematically compare the results of these screening theories. And that, to my mind, is the interesting opportunity offered by these transition metal dicalcogenides. Right? So, as I said, these are two atomically thin layers put together in such a way that they make a big unit cell. Now, I want to tell you just a couple of details which will be relevant later. All right? The first thing is that when you do this, the states that you care about are the ones which are shown in red here, which are at the top of the so-called valence band of the material. Right? These states are characterized by a very strong spin-orbit coupling, which splits the states. So the ones shown in red have only spin up with respect to the plane. The band just below it has states only down, and there's a negative momentum in which the spin assignment is opposite. Okay, so when you put these things together, what you find out is that you get a much larger unit cell, therefore a much smaller Brillouin zone. And the states in this much smaller Brillouin zone are drawn in an interesting way from these 2 points in the band structure. All right. And what this means is two things. First, well, the most important thing it means is the following. One of the experimental parameters in this system, apart from the total carrier concentration, is a potential difference between the top and bottom layers. if there is no potential difference, then to good approximation, this system has a slightly complicated inversion symmetry, NC6. However, if you turn on this field, you break the inversion symmetry and dramatically rearrange the band structure. All right. So in particular, when you break the inversion symmetry, you separate the spin up and spin down bands near at most of the wave vectors in the Brillouin zone of your new system. And you rearrange the density of states substantially, and in a way that can be controlled by application of an external field. Okay, so now if I look in detail at the electronic structure, all right, what you find is that the relevant states, the ones at which can be occupied by a small number of holes, form a simple band more or less separated from other bands. So the band separation problem is easy to deal with. Second, in the same way, most of the screening transitions are at high energy, are well accounted for by normal methods, and can further be controlled by the other things you put in experimental devices, so that the interactions are essentially known and the band structure is essentially known, and both of them are controllable. And that's discussed in the papers that are listed on the upper right here. Okay, so that gives you an approximate theory, which you can then proceed to analyze by these embedding methods. All right, so we did this, and by we, I mean Jiawei Zhang, really. Right, so you apply this embedding method. What you discover is that in the inversion symmetric case, phi equals 0, you have, as you change the strength of the interactions and temperatures, a phase diagram which features paramagnetic metal, magnetic insulator, and paramagnetic insulator phases. As you change the displacement field, thereby changing the band structure, you move the phase boundaries around in the ways that are shown. You also, although I'm not going to talk about it in very much detail, change the magnetic properties from something which is approximately SU2 spin symmetric to something which has a XY anisotropy. Okay, so then you can further apply these embedding methods to calculate physical quantities such as the resistivity. I've shown this here. Right? And what you see is that you have a metallic phase where the resistivity is low and increases as you raise the temperature, an insulating phase where the resistivity is high and decreases as you raise the temperature, and intermediate cases where the resistivity is non-monotonic. Right? You will see some little X's and crosses on these things. That shows where the theory predicts magnetic transitions. Okay. One of the interesting things conceptually about these materials is that because the intrinsic electronic energy scales are so low, they give you a look at temperatures which are high compared to the intrinsic electronic scales. That's something which you don't have in normal materials. So we can look at temperatures which are high compared to the coherent scale and discover that the resistance is approximately linear in temperature with coefficients we can figure out. Okay, now, I think that I will skip this and just say that as you change your band structure, you can make the low temperature resistivity in the metallic phase go from quadratic, which is what you expect in a typical metal, shown by the solid line here, to linear, shown by the dashed line. These are calculations, again, performed in the paramagnetic phase. The little red X's show where the theory tells you it's to be magnetic. Now, just as a sidebar, doing these calculations, it still requires solving a quantum many-body problem. This is done in so-called imaginary time. You have to do analytical continuation to obtain real frequency information, including the scattering rates that give you the resistivity. Right? Analytical continuation, as you probably know, is a classical ill-conditioned problem and is subject to many uncertainties. And it therefore has to be tested in all kinds of ways. What I've shown here on the left is just tests of different methods of analytical continuation. And again, I'm happy to discuss this in detail later, but I think we have fairly firm evidence that the results that I'm showing you here are not artifacts of analytical continuation and are correct. Okay, So you can examine the resistance in detail. You can see crossovers from linear to quadratic, and so on. All right, so now I should like to compare these to two experiments. There's a group led by Augusto Giotto, who's a graduate student at Columbia with Abhay Pasupathy and Corey Dean, who looked at the twisted homobilayer, which has this extra phase degree of freedom. And then there's the group at Cornell of G. Shan and Kinfei Mak and collaborators, who looked at the material where the large unit cell is made by a lattice mismatch. Right? Now, in the homobilayer case, basically they can change the interlayer potential, which they call D. And what you find is a metal insulator transition that occurs for densities of electrons around 1 and for particular values of this displacement field. And for carrier concentrations near this displacement field, you get a resistance which is linear in temperature until the thing thinks that it's insulating. Right? So you can compare that to our calculations, and what you find is semi-quantitative agreement. To remember resistance in actual units. What we find is a linear resistance above the transition, which has, trust me, the same slope as in experiments. A metal insulator transition, which is tunable by the displacement field. Right? And a crossover from linear to quadratic resistance. All of these things are seen semi-quantitatively in experiment. The two things which are clearly different from experiment are, first, as you can see on the left, the experimental resistivity is characterized by a strongly parameter-dependent offset. And that strongly parameter-dependent offset is not present really in our theoretical calculations. The second thing is that the behavior as the resistance becomes insulating in the calculation is much more pronounced than in the experiment. And whether these are problems with the simplicity of the embedding theory we're using and the basically mean field nature or something else is now under investigation. Right? Now, if you look at this other material, here changing the electric field, for reasons I don't have time to explain, between layers, changes in effect the ratio of electron bandwidth divided by interactions. And what you can see is that changing this thing causes a metal insulator transition. So if you keep the electron concentration at 1 per unit cell, you tune this electric field, you tune the material from metallic to insulating as shown here. Right? Here are our calculations obtained without adjusting anything except to put the maximum of the green curve at the same place as the maximum of the green 0.66 curve in the experiment. Right? That fixes the temperature scale, basically. Nothing else is adjusted. And what you can see is that there is a remarkable correspondence between theory and experiment in terms of the approximate magnitude of the resistance, the change from metal to insulator, the shape of these curves. There is one pronounced difference again. The theory predicts a magnetic transition shown by these crosses. And I think it's fair to say that there is no sign of that metal insulator transition in the experimentally indicated data.
Can I ask you a question?
Yes.
So in all these calculations, the starting point, is it the ab initio calculation or is it some sort of a BM model?
Well, it's ab initio, but not very ab initio is the way I would put it, right? So what ab initio buys you is, basically what ab initio buys you, let me just go back to here, is the curve shown here. All right. And then we did this pulling out the correlated orbital that I defined to focus only on the uppermost of those bands. All right. Then you have to get an interaction. And there it's somewhat more ad hoc. We have approximate estimates using the methods that I described. But in practice, there is a large amount of screening controlled experimentally by the precise way the device is put together, and the other stuff they put around these materials in order to keep them, hold them together, prevent them from getting destroyed by environmental contamination and so on. And that contribution to the screening is something we don't know. So we get interaction I would say really from quote ab initio to not better than a factor of 2, and after that it has to be adjusted.
And a related question is that for this type binding-ish model, and to do DMFT, you need to localize some of the orbitals. Is that right?
Yeah. So if you like, what we did was we took the top band here, we Vaunierized that guy, and then we projected the DFT Hamiltonian onto those states.
Is there some sort of a topological fragility going on with this?
Okay. Excellent question. No. Not in these particular systems. I should have highlighted that. That's one of the very interesting things about these systems, is that depending on exactly how you put them together, you may or may not have a topological obstruction to exponentially localized Bonnier bands. You may or may not get churn bands. These are the cases where you don't get it, basically because you have to start somewhere.
Does this factor depend on the twist angle, or?
It depends on various things, including the twist angle and the degree to which the layers are compressed.
So the calculations are performed for the cases where you can do exponential.
Yeah, I would say the DFT calculations have been performed for a much wider range of cases. The experiment doesn't have any signs of churn numbers, and we built the many-body theory on top of the topologically trivial one of the DFT calculations. But just to go on, in my view, exponential localization is overrated. I mean, this is something that we're doing right now, but basically you can, once you have a topological obstruction, you have Bonnier functions which are power law, not exponentially localized. But all of the theory I described goes through in exactly the same way. It's, in my mind, a practical question, once you have that, how good the locality approximation is that I used to solve the correlation problem. But that's a practical question. Conceptually, all this will fly. This is work that's in progress. I don't have a demonstration I can show you, but I believe that to be the case.
So if you truncate that prematurely, is that possible that it would destroy some of the symmetries, which only holds?
Wait, I'm sorry, say that again.
So if you truncate that, let's say with a slower decaying one-year function, is that possible that the resulting Hamiltonian loses some of the symmetry properties that are important?
Right. This is a separate topic, and because we haven't published it yet, I don't want to go too deep into that. But basically, no, there's a way to do it without losing any of the symmetry properties at the cost of having these power law decaying wave functions. And the basic question is, how good in practice are the locality approximations if you apply them to wave functions which are power law localized and not exponentially localized? But there's a way to do it that retains all the symmetries at the cost of having power law localized things. Right. Now, yeah, anyway, but at least let me put it this way. Conceptually, there's a way to do it. We still have to see if it actually works. All right, where was I? Yes. So another thing, look, you see these data, and there's a clear transition from metal to insulator. And when a physicist, at least a condensed matter physicist, is confronted with a transition like this, the first thing they like to do is scale the data, right? So the idea is, the question is, by adjusting the temperature scale and the resistivity scale in some way, can you collapse these curves on top of each other? Is, let's say, the purple one the same as the black one if I just stretch the temperature scale by a constant factor and compress the resistance scale by a constant factor or something? All right. So the experimentalists did that. All right. They essentially take one curve, which they identify as the critical curve. They divide all the resistances by that and then adjust the temperature and resistance scales. And they get the data to collapse fairly nicely, as shown on the left. And then you can infer things about the behavior of the energy gap, which causes the resistance to go up, or the characteristic temperature scale associated with the metallic behavior when the resistance goes down, right? So you can take our theoretical calculations and do exactly the same thing. That's what's shown in the middle right panel of this thing. And because we're theorists and have numerically very accurate data, we can get a really very impressive scaling collapse, right? So all of these things are consistent, and they suggest that there is some kind of interesting critical behavior associated with this metal insulator transition, right? As was noted about 8 years ago by Vlad Dobrosavljevic and his collaborators. So basically, on this level, everything more or less works, right? With 2 points that I wanted to make. First, as I said, the experiment doesn't see magnetism. And second, if you go back to these curves, which are really on the same scale, our high temperature resistance is high 10 to the 4, getting close to 10 to the minus 5, whereas the experimental resistance is high 10 to the 3, low 10 to the 4. The theoretical calculation is clearly overestimating the resistance by a factor of about 5, right? Although all the qualitative shapes are nice. So there is something there to be understood in the fundamental question of how do you calculate the high temperature resistance of an interacting system. Okay, so this is basically what I wanted to say, that I gave you my practicing physicist, possibly idiosyncratic view of embedding theories and what the limitations are. And then I argued that these new twisted TMDC systems provide a very, let's say, conceptually and intellectually important base for analyzing the practical effectiveness of these theories. And clearly there's enough agreement to make this kind of thing a good base to build further investigations on. So with that, I will stop and thank you for your attention.